from our groups? Looks good. Oh.
Jack's right here.
Oh, that's right. Okay. And I just pulled out the corrections, Jack, so that we can get that updated. If you guys did not know this, I did update Rhineland this weekend, so go check that out. What has not been updated are the points back from the corrections. The corrections themselves have been graded as far as whether or not, as long as they were turned in at the normal time, as to whether or not you did corrections on the problems you were supposed to. I just haven't gotten the 1/3. That would be nice, because they can go to 1/6. The 1/3 points back on your test yet. But they're coming, I promise. I just needed to eventually be like, enough's enough, update all the random grades, and then I'll get the other added in. Let me know, email me, best way, if you have any questions. All right, cool kids, with that, here we go. We are dealing with vectors, but we've gotten beyond the basics, which was section 6.3, right? Now we're to the beyond basics, which is section 6.4, dot products. Dot product, hold on. A dot product is talking about multiplying what two things?
U and V.
U and V, so they're both vectors. So we're multiplying two vectors together, and to do so, how do we do that one? Thomas.
U1 times V1 plus V2 plus V2.
Good. So multiply the horizontals, multiply the verticals, add. It's a number, right? And now we're seeing how that number can be used in all sorts of different ways. And one of them is to keep us from having to do all the geometry of drawing through the vector diagram and shifting and like making parallel lines and alternate interior angles and all that jazz. Log sines, log cosines. We get to avoid all that with the dot product because we're able to actually use this formula that says, hey, I'll find theta for you, the angle between two vectors, by plugging and chugging. Hopefully you guys double checked the work on Friday. We were going really fast at the end. What angle did you end up getting with cosine inverse of 3 over rad 13?
33.690.
690? Thomas, you backing up?
Yeah, that's good.
Good. Thanks, Becca. 33.690, the angle between, done. Didn't have to draw a picture, didn't have to shift, didn't have to do anything crazy. So I like that one. But the problem is, it's in the yellow box. If you don't know it, can you use it? No. Like on a test, for instance. So, okay, hold on. What formulas do we have so far? We have law of sines. That's this chapter, right? We have an area formula. We have law of cosines. We have an area formula. We have vector addition, but that's just like adding the horizontal verticals together, right? We have how to find magnitude using Pythagorean here of a vector. We have how to find the direction, which is the angle, using what trig function are we using for vector angles if we have the components? Tangent, because opposite and adjacent are the two sides that we would have, the horizontal and the vertical. So we've used tangent inverse. Just beware the quadrant. Let's see, what else do we have? What if we don't have components, but we like using them because they help us avoid crazy stuff like the big old nasty geometry stuff. So we can avoid all of the parallel lines and all the needing to shift, etc. if we just get components, but where did these components come from? Are there formulas to help us?
Yes.
Yeah, what's the formula say for the horizontal component? Who's this guy? Magnitude times cosine of angle, right? And then magnitude sine angle. We get the components, we can add them together, we can use Pythagorean, we can use tangent inverse. That's a great problem. Anyway, let's keep going. Then the next formula that we saw was dot product, which is kind of easy as long as you don't get confused. Multiply the first, multiply the last, add it all together. And now we have the cosine, the cosine of theta equals u dot v all over magnitude u magnitude v. Okay, what's this whole orthogonal thing? What does this say orthogonal means? You guys catch it? Yeah, so two vectors are going to be orthogonal to each other, are going to be perpendicular to each other, if and only if their dot product is 0. Because think of it, for the dot product to be 0, doesn't that mean that u1 v1 plus u2 v2 has to equal 0, right? I'm not sure if I can fully explain this without using the next formula. There's one other formula called projection. I think this one kind of gets the idea a little bit more across as to what's going on with dot products. Because this one says if you have a vector working not perpendicularly, or it's not perpendicular to another vector, what ends up happening in a perpendicular way, projecting with it, or how is it affecting the perpendicular overall effect? This is a little easier because the projection will only be 0, hence the vectors will only be perpendicular if the dot product is 0, but I don't know if that really helps. Long story short, we can do the math. And we can see the angle. Another way of looking at it is the following. If they're perpendicular to each other, what would that mean about cosine of, oh hey, wait a minute. We just talked about that formula. Cosine of, maybe it'd be easier to go back to the formula before instead of forward to the next formula. And we'll vector arrows in. You guys still drawing your vector arrows?
Yeah.
We don't need to do it on U1, U2, V1, V2 because those technically, too far, struggle, are vectors. Those are the components, but check it out. If they're perpendicular, what would that mean the angle between them is? 90. So let's think about that. Okay, well hold on. Perpendicular, cosine is 90. What is cosine of 90?
1.
Oh, there we go. Maybe that's a little easier way of looking at it. If they're perpendicular, the angle between them is 90. Cosine of 90 is 0, which means this whole side has to be 0, which will only be true when the top is equal to 0. So did anybody actually go through and do the example? Because we just had to take a dot product, right? Although it's written weird. Does it help anyone to write it in like a nice little side brackets? Okay. How would you rewrite the components of u if all they put was vector u equals vector I? Good. The I is there, so there's one I. But the j is gone, which means 0j. Okay, what are the components of the second one? Using the I and j notation. So if we were to do the dot product of u and v, we would do 1 times, I'm just showing the work for those of you guys that are still getting the hang of it. But my question is, are these two vectors orthogonal?
No.
Which means if we did want to find the angle between them, first of all, we can say no, they're not orthogonal, aka they're not perpendicular. If we did want to find the angle between them, we'd have to revert back to this guy and say, all right, what's the angle? I don't know, let's plug in. Oh, sorry. My bad, I didn't put the not. My bad. Because this dot product ends up being -2, right? Thanks. Which is not 0, therefore, angles that theory, not orthogonal, done. All right, this is the last, I'm almost positive this is the last one. Yeah. Projection kind of leads to work, and work kind of leads to the word problem. So, projection, let's put it this way. One of the most common word problems that has to do with projection, actually projection leads to work, is, for instance, imagine there was, I don't know, what could it be? A semi-heavy box, don't make it too heavy, I'll hurt my back. A heavy box on the ground. There was like a rope tied around it, and it was too heavy for me just to like, well, I didn't want to kill myself, lift up and then go over and put over there underneath the table, okay? Why would there be a rope wrapped around it? What am I going to try and do?
Hold it.
I'm going to try and drag it across, right? Theoretically, that might be better on my back than you like going down and like dragging it. So anyway, question. Where am I asserting, or where am I putting all of my effort?
Shoulder.
Through my shoulder into the rope, right? But what's the rope attached to? The box. So is there tension along the rope? Yes. Am I pulling up on the rope? Yes. But am I trying to lift it? No. What am I trying to affect? What am I trying to end up doing? What's my goal? To move the box. But that's weird, because when I move the box, isn't it going to be sliding along the ground? So by me pulling diagonally, I'm trying to move the box horizontally? Yes. That's an idea of projection. Here's one that kind of seems to fit the case that I'm telling you. I'm pulling the rope this way over my shoulder. I'm pulling this way, but in essence, I'm trying to project that force on the movement of the box horizontal. Does that kind of make sense? So I'm pulling diagonally, but what I'm trying to do, what I'm trying to result, what I'm trying to end up accomplishing is projecting all of that. How about right behind Kathy?
What?
That way you guys are kind of spread out. Just make sure desk is clear. Thanks, sir. But what I'm trying to do is project that effort onto the box actually moving the way I want it to go. So this formula, the projection of U onto V, the idea is, hey, I am doing this, and this is just one example, but here's this vector that's working in this direction, but what I'm trying to do is figure out how does that project onto this secondary one, like which is vector V. The formula is pretty straightforward in the sense of, okay, I do a dot product, I divide by the magnitude squared. The crazy thing is, guys, this whole piece right here is really just a constant. You'll end up getting a scalar. The dot product is a constant, the magnitude is a constant, so this will all just be a constant, and so I'm going to multiply that constant by the vector. I'm going to actually end up with a vector as my answer. Because in this formula, I'm not just trying to get a set number, like, I don't know, the measure of an angle, or the dot product alone, which is just a constant itself. I actually want the overall, in a sense, result. I don't like using that word, though. I want to get the new vector, which we call the projection. The overall result of this work being done on this projected onto this vector down below. So when they give us something like this one's kind of weird because the whole thing is tilted. You can't exactly say like, oh, the box is going across the horizontal surface. But maybe we could think of another example, like, how would you do that? What's the projection of U onto V? This is U. It's important that you have the order also. And this is V. Because as you guys also notice, the formula itself, not only does it affect how we write the projection, in that U goes on to V. V is like the little subscript, U is the argument, but we also have to be careful that we want the dot product of U and V. That's not a big deal. But we only want the magnitude of V squared times that vector V. So this vector is being projected on how does this movement or force, how does this affect what's going on to this guy down here as far as the overall. You guys know dot products? What would the dot product be of these two guys? Good, 12 plus, oh, negative 12. That means, what does that mean about these two vectors if the dot product is 0? Yeah. Orthogonal. Okay, so the dot product is 0. What's the magnitude of vector V? How do I do that? Good, Pythagorean theorem with the components. So that would be Pythagorean theorem squared using my formula. And that would be 2 squared, which is 4, plus negative 3 squared, which is 9. And I'm multiplying that by vector V, which is 2, negative 3. But what do you guys notice is going to happen anytime the two vectors are perpendicular?
It's gonna be 0.
One way of thinking about it could be, remember how I just said the box was too heavy for me to lift and put over under the table? So the rope was my way of doing it? Question, how helpful would it be if I was standing over the box, like my shoulder was over the box and I was doing this? Is that going to help me at all? That would be a perpendicular. I'm trying to pull this way. The box is literally right below me. How is that going to help it get over there at all? So the projection of what I'm trying to do is not affecting any change or any help on the movement I'm trying to do. Yeah, at that point, just pick it up. So there would be no point of the rope at all. That's kind of something, or a silly way of kind of visualizing that idea. So that's projection. It's obviously not always 0. It's usually not. The only time it's going to be 0, like, oh, well, that doesn't really affect anything. The only time it's going to be 0 is when, once again, they are orthogonal or when the dot product is 0. So just to let you guys know, if you get the dot product to be 0, double check your math. It's very possible. It happens from time to time. Last one. Last one. There's a hard way of thinking about work, and then there's an easy way about thinking about work. For anybody who's taken physics, or maybe even back in physical science, you might have been rocked just a little bit by the idea that if there is no movement, work is not actually done. If there is no movement or motion, we aren't technically able to say that work is done, because work is defined to be force times distance. So you could be pulling and pulling and pulling on a box all day, but if it doesn't move, technically we could say, well, you didn't do any work. Like, well, I'm sweating like I did work. Well, you exerted effort, true, but technically, in the definition, the scientific definition of work, we say, nope, no work happened unless there was movement, there was distance along which that force was being exerted. It's kind of crazy, kind of hard to think about. Once again, praise the Lord, this isn't a physics class, but if work does equal force times distance, the idea is, if I'm exerting this force, here's my box example, through the rope over my shoulder, that's great and all, but I need the force to be in line with the distance moved. That's what this formula is trying to say. I need the force to be in line with the distance moved. So yeah, that's great, you're tugging on the rope, that's good and all, but I can't multiply that force, the force I'm exerting with the rope on the box, I can't multiply that times distance because that doesn't work. I need the force to be in line with how the box is moving. And so it is a kind of basic force times distance formula, but when I have this vector or this force being exerted at some angle to the original, or to the direction it needs to go, I need to project that down so I can then have the force, which we would call the projection, to multiply by the distance. So you can kind of see down here, it's like, okay, force, yeah, but I need the projection. I need the, however the force is, which is at an angle to the movement, I need that projected down onto that line of motion, and then once I get that force, now multiply it by the distance. And the distance would be, well, the magnitude of however far, the length, you could say, of however far the object is actually moved. So that's one way of looking at it. A simpler way of looking at it is force times that vector that shows the length. So force times the vector that shows the distance that's been moved. Just remember that force needs to be in line. So as we get down to the example down below, let me zoom in. You guys don't, you have a projection formula, right? That's okay, we can recall it if we need to. Let's go figure out what's going on in this example. Let me make it so it's a little bit bigger. Find the work done in moving a particle from P to Q. So where's my initial point? P, good, from P to, where's my final point? Q. When the magnitude and the direction of the force are given by vector V. Are given by vector V. Okay, so what can we do? No, we don't want to add P plus Q. We could figure out the components of PQ. Do you guys remember how to get the components of PQ? If they give us the beginning point and the ending point, how do we do that?
Square root, or is it one?
Square root is magnitude, but before magnitude, we need the components, the x and y. I could just graph 1 and 3 if we needed to. I could just graph negative 3, 1, 2, 3, 4, 5. And it's from P to Q, so the arrow's going this way. But I need components. I mean, could I graph it super nice and could I measure the across and then the down? Yeah, but how can I do that mathematically without even needing a picture? Subtract. Yeah. And you do the final point minus the initial point. Remember that from the beginning of vectors. Final minus initial. So I'm going to get negative 3 minus 1 It's been a while since we had to do this, huh? And then 5 minus 3. So the final x minus the initial x, and the final y minus the initial y. But the settings just changed because it just got really cool. So I have the components of PQ. Oh, no, it's still the same. Okay, build character. Okay, now what? You're welcome. I need work. What can I do? I have the components of PQ. Which one looks more fun? Does it look more fun to actually go through the whole idea of getting the force in line and then multiplying the magnitude of the projection onto the magnitude of the distance and having to find the projection using that huge formula? Or does it sound better just to do a dot product between the two? So which one do you think we're going to start? This guy. Which one are we going to like? This guy. Because what does he say to do now? Take this guy and that guy and do it.
Multiply.
Got it. But multiply with the dot products, right? So let's rewrite this vector v just in case some of you guys still don't like the I and j, the linear combination form. But, oh, well, that's really all we have to do. Yep, that's really all we have to do. Could we have done it the long drawn out way? Yes. Would it have gone through all the concepts of how work works with force times distance? Yes. Is the dot product super snazzy and neat because it just helps us solve it way faster? So how do we do that? Well, horizontal times horizontal.
14.
Get into 14, we have 8, and then vertical times vertical. Got it. Nice.
That's how much force you did?
That's how much work is done. When a force that's acting in the direction of -2, 3 is resulting on the object that's moving from P to Q.
What is the actual unit? It's just force.
Well, they didn't really give us what they were measuring. This is what we need, because this would be distance, so we would need to know is this feet, is this miles, is this, so we don't know the unit for the distance, and we don't know the unit for the forces that they're giving.
Okay.
But work ultimately ends up being, is it newtons? I think work is, or is it newton meters? Wait, force times distance, I think it's newton meters. Yeah, and weird capital N, little n. Take physics. Okay, so, how about this guy? How do we use the idea of work and what we just saw? You can take a dot product if you figure out what to take a dot product of. For this example, a tractor pulls a log, not a logarithm. 800 meters. You're welcome. And attention, in the cable connecting the tractor and the log is approximately, hey, newtons. That should be a capital N. I apologize. 15,691 newtons. Way more tension than I would ever give. The direction of the force is 35 degrees above the horizontal. Approximate the work done in pulling the log.
Oh, sorry.
Sure. So, for the tractor.
800.
Then he had to pull it. Looks like a train. Anyway, so we have a tractor. You're welcome. Maybe he's too long. Anyway. You should know this one. Anyway. We're just done. Okay, so anyway, that was the door I had to keep up. So, where's my log? There. Okay, so, what do we got?
The tension is 15,000.
Very dense log. Alright, so what angle do we have?
35 degrees.
35 degrees. Can I try to draw logs? People make fun of me, so I just don't. We have 35 degrees, we have our log here. It's so big, and we're so far away, so let's look at that. Although the tractor is huge. Anyway, 800 meters, right? That's a thing. That's how far it gets dragged. So we'll say that the tractor keeps going, and it drags the log, I don't know, a total of whatever it is. We'll split it there. Work equals course times distance, but when we're dealing with vectors, it doesn't really change much. Can tension be seen as force? Yeah. We've used that a couple times in section 6.3 and 6.4. So,
Law of sign.
law of signs. Well, A, it's a right triangle. I'm not really sure we want law of signs.
Never mind.
Makes it a little easier. But B, Pythagorean theorem, I guess we could find this little opposite side, but I'm not sure we need him, do we? What do we need? Do we know distance?
Yes.
Okay, we know that's 800.
840.
But what, can we just plug in 15,691 newtons?
No, it's at an angle.
It's at an angle. Okay. So, but law of sines, we don't need it. It's a right angle. Right triangle. Oh.
We don't need it.
So how are we gonna? We have the 800. Technically, we could be super snazzy and say that the distance, if it helps, because think dot product, right? We could say that the distance is, I'll write over here. You see why I'm putting 800 and 0? Why am I putting 800 and 0 for distance? It goes straight horizontal, so I could, if I'm doing a distance vector, I say, okay, cool, there was movement 800 horizontally and 0 vertically. Now, how can I make a vector for the force if it's being exerted at an angle of 35 degrees to the horizontal? How do I get components if I know direction and magnitude? As you guys are looking, let's see if you can find what I'm already putting. You guys agree?
Yeah.
So the problem was, I wasn't given components, so I couldn't, in the last problem, I was given components. It was like easy cheesy, well, it's down there, but I was given components, I could just do a dot product. This one I needed to get my components. The horizontal distance was easy, 800 0, because it didn't move vertically, it just slid along the ground. But for the force, the tension, and what it affected being at an angle of 35 degrees, I had to find it myself. But now, what's the name of the game? Dot product, yeah, plug and chug. So W is equal to horizontal times horizontal, right? 800 times 15,691 cosine of 35 plus 0. How come 0? Doesn't matter, this guy's times 0. So as you guys are plugging and chugging, maybe you can figure out another way of doing this would be, in a sense, the projection, but it's easier, would be to solve for the adjacent using cosine. Cosine of 35 is adjacent over hypotenuse. You could have also just realized, hey, I have the distance of 800. I need the force to be projected in that same direction. So if I just solved for the adjacent side of my triangle, I would have the force to multiply, which ends up being the exact same thing. And what did you guys solve when you got work? It's probably pretty big.
10 million.
10 million?
282,000.
82?
Yeah. 651.
Point
780.
780. And my units, well, the force,
Newton.
or the tension, which results in the force, was newtons, and then the length was, hey, look, I was right, meters. Looks awkward, but it's right. With that, kiddos, we are done with section 6.4. Basically, we learned what a dot product was, and we're like, hey, guess what? There are tons of things you can do with the dot product. There are tons of things you can do with the dot product. Our goal, finish 6.4 and start 6.5.
Can we go back, please?
You can take a picture of it. I'll leave it up here for about 5 seconds. 4, 3, Cool. Remember, you also have your group members on either side. Okay, 6-5. It's the final section of chapter 6. We're going to start it today, finish it tomorrow after grading our 6-4 homework pretty quickly.
Right.
So guys, don't just dabble in the 6-4 homework. Try it. You should have done the majority of it over the weekend. And when you get stuck, go check out Calc Chat on the on, see if you can kind of piece together from the formulas in your notes. Please have your notes close. Don't try to do it by yourself. Have your notes close, have the examples in the book close. And then come with good questions of ones that you got stuck on, okay? But otherwise, we do need to keep on going in 6-5. 6-5 seems kind of random. So it's like, oh, hey, let's talk about imaginary numbers again. What? I don't get it. Why are we talking about imaginary numbers? A plus B i's. Well, the math dealing with complex numbers has a lot in common with the math dealing with vectors. The vectors have a horizontal vertical component, an A and a B. A times an I vector, B times a J vector, and complex numbers say, oh hey, I have a real part and an imaginary part. And I have to keep those separated also. I have a real part and an imaginary part, and I need to keep those separated also. And if you guys remember, we used to graph those with the real part being the horizontal and the imaginary part being the vertical. And even though we wouldn't necessarily draw an arrow, we still would have a diagonal that we could break into horizontal and vertical pieces. And if we think about absolute value, and I think we brought this up last year, or not last year, last week. Last week. Patricia, I think you answered it. The absolute value is the distance from 0, so it's kind of like the magnitude of the number. We can actually then say, well, hey, with all this work from vectors, if we're looking for the magnitude of a complex number, aka the absolute value of a complex number, we're going to use basically the same math that we used for the magnitude of a vector. If we want to find the distance between the origin and the point AB, that's the magnitude of the complex number, we're just going to use Python. But we kind of waited until we did some vector work so that this wasn't quite so foreign of an idea. So the notation's a little different. It's not double bars like the vectors. But that's also because it's a type of just number. It's not a vector at all. It's a type of number even though it has imaginary parts to it. So right down here, if I wanted to take the absolute value of 5 minus 12i, a lot of kids would think, oh, okay, 5 plus 12i. Make it all positive. But that's not what it's talking about. It's saying, no, this isn't just like a single number. This is an actual like horizontal vertical location on a real imaginary axis on a complex plane or a complex graph. So the way to find the magnitude, I need to do Pythagorean, where I do 5 squared. Now careful, we're not doing bi squared, we're just doing the coefficient. So I'm just going to take the negative 12, not the I. What's Pythagorean with the coefficients? I end up with, what's 25 and 144? Yeah, 169, and isn't that a perfect square root? This is a 5, 12, 13 triangle. It's the 5, 12, 13 triangle. So just like there are magnitudes of vectors, there are also magnitudes of complex numbers that say, hey, thinking of the real component and the imaginary component, and thinking about the overall magnitude of the number, I just have to use Pythagorean. I just have to use Pythagorean. And, whoa, this looks weird. Unless we realize, isn't this just, hold on. Doesn't this look a lot like my vector math with r cosine theta and r sine theta, and who's r? R is the absolute value of a plus b, which is the magnitude Theta is my direction. And if we needed to go from one to the other, we could literally just use my same formulas as we use from vectors. So guys, some of the letters change, but a lot of the math remains the same. It's just applied to something different. And remember, with imaginary numbers, that has applications in like electricity and currents. It's on again, off again, or like switches, like binary code, on and off, ones and zeros, real and not real, depending on the powers of I. So anyway, we're gonna play more with complex numbers tomorrow. But what's your goal tonight? Finish 6-4, and if I were you, keep studying your formulas. Bye guys.
Why is Brian? You know what?